What exactly is neuromorphic computing, and what does it have to do with studying the cosmic microwave background, which is the electromagnetic radiation left over from the beginning of the universe? Neuromorphic computing replicates neurobiological structures seen in the nervous system using extremely large integration systems with electrical analog circuits. Some physicists and researchers have proposed a hardware platform comprised of superconducting optoelectric circuits for the implementation of neural networks and large-scale neuromorphic computing. To replicate spiking neurons, the system integrates semiconducting few photon light emitting diodes with superconducting nanowire single photon detectors. The South Pole Telescope, an observatory with a 10-meter diameter that is located at the South Pole in Antarctica, was built to study the cosmic microwave background and is one example of an imaging system with superconducting sensors that are particularly well suited to integrating with other cryogenic technologies. The South Pole Telescope makes high angular resolution maps of the temperature and polarization of the cosmic microwave background using a superconducting bolometer with a powerful electrothermal feedback, millimeter wave grouped element superconducting bandpass filters, and superconducting transition edge microcalorimeters. The development of neurocomplementary metal oxide semiconductors, including optical communication above a certain spatial scale, could aid in the success of superconducting optoelectric networks because it will be advantageous for them to interconnect with complementary metal oxide superconductors via photonic signaling on fiber optic links between cryogenic and ambient environments. Before I finish, I want to discuss one final instrument and emergent phenomenon that could use neuromorphic computing to improve our understanding of the early universe. And that instrument is based on the Josephson Effect, which is a phenomenon in physics that happens when two superconductors are put close together with a constraint or barrier in between them. It is an illustration of macroscopic quantum phenomenon, in which quantum effects may be seen at a macroscopic level rather than an atomic level. Josephson junction-based neurons could pinpoint the precise dynamical mechanisms underlying a system's neuron-like characteristics and reveal new complex behaviors that are important for neural computation and the use of superconducting neuromorphic devices to better understand the cosmic microwave background. A Bogoliubov quasi-particle is a quantum of energy in a crystal lattice or other system of bodies that has momentum and position, and may be thought of as a particle that happens in superconductors in particular instances. When a macroscopically complex system, such as a solid, acts as though it contains several weakly interacting particles in a vacuum, these Bogoliubov quasi-particles and collective excitations develop. In order to measure the polarization of the cosmic microwave background, which could then reveal information about the primordial gravitational waves that preceded the photons emitted from the early universe, Daniel Flanagan of Columbia University has suggested using kinetic inductance detectors, a type of superconducting thin-film microresonator that is sensitive to photons and a number of Bogoliubov quasi-particle excitations in a superconductor. Observation of parity-induced suppression of Josephson tunneling in superconducting single electron transistors could be used for these particular quasi-particles that may also become trapped in local defects in normal metal regions in contact with the superconductor. According to experts, the circuit of two manually coupled excitatory neurons has been analytically and empirically investigated. A superconducting quantum interference device, which is also utilized at the Simons Observatory to detect the cosmic microwave background, was employed to mimic a synapse. Josephson junctions were also used to create each neuron, with a Josephson transmission line serving as the axon and the Josephson junctions serving as the junctions that are analogous to neurobiological processes.